In this last presentation on forces, we look at an object that's in free fall and then also an object that is falling and experiences air resistance during the falling motion. So when an object is in free fall, the only force that's acting on it is the force of gravity, and under those circumstances, the object accelerates at -10 or 10 meters per second squared downward, and this is from the acceleration due to gravity. And all objects will fall at this rate in the absence of air resistance. But when air resistance is present, there's actually an additional force that acts like friction that's in the opposite direction of the motion. And because of that additional force that's acting opposite the force of gravity, the acceleration is actually less than 10 meters per second squared. So let's look at free fall, where there's no air resistance present. And suppose that I took a brick, which is very heavy, and a tennis ball, and I released them both from rest. And so what I know is that the force of gravity on the tennis ball is less than the force of gravity on the brick. And so that's why the arrow here for the force of gravity on the brick is larger. There's no air resistance present, so the only forces that are acting on either one of these objects would be the force of gravity. So if I apply Newton's second law, which says that the net force is equal to the mass times the acceleration, regardless of which of these objects I look at, the only force that's acting is the downward force of gravity, which is mass times gravity, and then the direction is negative because it's downward, and that has to equal the mass times the acceleration of the object. So even though the masses are different for both of these, that force depends on the mass times the acceleration, so the mass actually cancels off on both sides of this expression, and I get that the acceleration for free fall is just minus the gravitational acceleration. And so regardless, as long as there's no air resistance, if I dropped a brick or I dropped a marble, a tiny marble, they would both fall at exactly the same rate of 10 meters per second squared downward in the absence of air resistance. But what happens if there is air resistance? So air resistance is a force that opposes the motion. And so here's an example picture of my brick where my force of gravity is acting down and I have some air resistance acting up, and this brick is actually in motion falling down. So the amount of air resistance depends on how fast the object is moving. So the faster the object moves, the greater the air resistance is. It also depends on the surface area of the object. So a brick would actually have a larger surface area than a tennis ball. So in general, it would experience a greater air resistance versus the tennis ball. So air resistance is going to be larger the faster the object is moving, and it's also going to depend on, basically how big the object is, surface areas wise. So this object would experience, in this case, a net downward force of 20 newtons versus the net downward force of 50 if the air resistance wasn't there. So you've probably heard the term terminal velocity or terminal speed. And so what happens is when an object falls under the influence of gravity and there's air resistance present, eventually there's enough air resistance that the object can reach a point where it's not going to speed up anymore as it falls. And at that point, it's just going to continue to go at the same speed for the rest of the motion unless there's some force applied. So let's look at a picture of this brick where it's falling downward, and at this particular instant in time, it has air resistance of 10 newtons because of how it's falling. At a later time, after it has fallen faster, the amount of air resistance has increased to 30 newtons. So again, as it's falling faster and faster, that amount of air resistance is getting bigger and bigger. We'd like to know what is the net force that's acting on the object in each one of these cases. And so the net force is just the sum of the forces. So in both of these cases, I have an upward resistive force, and then I also have a downward force of gravity. So the resistive force would be positive and the downward force of gravity would be negative. So for each one of these, I can determine what is the net force. In my top picture, I have 10 newtons acting up, negative 50 newtons, or 50 newtons acting down, which is negative. That gives me a net force of 40. Versus here, I have more air resistance, and therefore I have, and then of course the force of gravity stays the same, so my net force is now negative 20. So as the object falls, air resistance increases, and as the amount of air resistance increases, the net force, so here's the net force, decreases. So I started off with a net force downward of 40, and now I have a net force of negative 20. I'm also interested in what happens to the acceleration. So as the object falls, if the net force decreases, the acceleration also decreases, because acceleration is net force over mass. Now, one thing I didn't say in this example was, what is the mass of the brick? Now, I know the brick has a weight of 50 newtons, so I can find the mass by taking the weight of 50 and divided by gravity, which is 10, so it's 5. So the acceleration of the block up here when the air resistance is only 10 is negative 40 over 5, which is negative 8 meters per second squared, versus when I get down further and I have more air resistance, I have less net force acting on it downward, negative 20, so my acceleration is only negative 4. So as an object falls, air resistance increases, net force value went from minus 40 to minus 20, it decreases, and whatever happens to the net force, that's the same thing that happens to the acceleration, so the acceleration also decreases. Now you can imagine that eventually, as this brick continues to fall, I don't have any space on my picture, but as this brick continues to fall, this air resistance value will keep getting bigger and bigger and bigger, and eventually the air resistance will equal 50 newtons, or it will equal the weight of the block. And at that particular time, when the amount of air resistance is equal to the weight, the net force is going to equal 0, right? These two values are equal to each other. They're going to cancel each other out. If the net force is 0, that means the acceleration is 0. So the acceleration kept decreasing. As it fell, the object is not, its acceleration value is getting smaller and smaller. Eventually it reaches 0. If there's no acceleration, that means that the object cannot speed up or slow down anymore. So it's going to continue to go at exactly the same speed. And if the speed of the object doesn't change, the air resistance isn't going to change, because air resistance depends on how fast it's going, assuming we don't change anything else. So we'll see something like that in another problem. But so in summation, right, as an object falls, air resistance gets bigger and bigger as it falls, and keeps speeding up as the object speeds up. The total amount of net force decreases, and therefore the acceleration decreases until it reaches a point where the net force is 0, the air resistance is equal to the weight of the object, and it reaches terminal speed. All right, so this is actually an example from Paul Hewitt. And so let's look at this example. We're going to do it on some other slides, but Bronco, who has a mass of 100 kilograms, skydives and parachutes from a stationary helicopter. So he's basically going straight down. And so we have different parts of his motion on the right here, where the air resistance is changing to different values, and we want to find the acceleration at each one of these points. We're going to start by determining the net force, and then we can determine the acceleration. Now this is actually a simulation or a little GIF file that sort of shows that motion from when he falls. So he's dropped, right, has acceleration, the acceleration downward keeps decreasing, he reaches terminal speed, and then he opens his parachute and the acceleration changes. All right, so here we go. So Bronco jumps out. He has a mass of 100 kilograms, which means he has a weight of 10 times that, 1,000 newtons. His air resistance is 0. So the acceleration is the net force. I have an upward force of 0, a downward force from the force of gravity of 1,000, divided by the mass, net force over mass, and I get an acceleration of -10 or negative g when he jumps out. As he falls, because gravity is pulling him down, he speeds up. And as he speeds up, his air resistance gets bigger. So now I have air resistance of 400 acting up, force of gravity of -1,000, or 1,000 acting down. That's 600 in the negative direction over his mass, and so he has an acceleration now of -6 meters per second squared. So he's not accelerating as much anymore. Then at point C, he reaches a speed that he's going so fast that his air resistance acting up is actually exactly the same value as his weight. Right? These two are equal. So the net force, when you add those together, is 0, and his acceleration at that point is 0. So Bronco has reached terminal velocity or terminal speed at that point, and he would continue to move at whatever speed he's moving at this point unless he does something. Right, so here we are, continuation of the picture. So he's reached terminal speed, but look at what he does. He opens his parachute, right? So over here, he decides it's time to open the parachute. And when he opens the parachute, that parachute now is catching some of that air. So he now has a larger amount of air resistance, right? So here's the air resistance. It's bigger than the weight. So my air resistance is now larger than it was. So it's 12,000 newtons. Subtracting off the weight, that's 200 newtons. Divide by the mass, and I get +4. So what does that mean? Oops, that's supposed to say +4. No, I'm sorry, this is supposed to say +2. This is supposed to say +2. So what does that mean? Well, he's traveling downward, but he's experiencing an acceleration upward. There's a net force upward. So the acceleration vector is opposite the velocity vector, which means that he's going to start slowing down. So however fast he was going, he's now slowing down. So now the parachute opens up even more, right? And so now the parachute is fully open, catching lots of air. Air resistance is even bigger. So now this is 2,000 newtons of air resistance minus the weight. It's got more force acting up. So he's actually experiencing an acceleration upward of 10 meters per second squared. So again, he's slowing down even more. He's getting to the point where, he was traveling pretty fast. Upward force is causing him to slow down. He's slowing down even more. Well, as he slows down, the amount eventually, with the parachute fully open, he's going to continue to slow down until his air resistance decreases. Right? So he's at this point right here where his parachute has been opened. He's slowing down, and as he slows down, the amount of air resistance decreases. So it went from 2,000, but because he's slowing down from that upward force, his air resistance has gone back down to his weight. So when these two forces are equal, he reaches terminal velocity again. So this is kind of a weird example. So he started off jumping from the plane. He's speeding up as he's going down. He reaches terminal velocity with his body. He opens up his chute. When he opens the chute, it catches more air, more surface area. It causes him to actually start to slow down. And when his chute is fully opened, he's really going to slow down. And as he slows, his air resistance decreases until it reaches his weight again, and then he reaches a new terminal speed. And again, this is written as +4, but this really should be 2, right? 200 over 100 is 2.